I am going to use the method described by Sierra 21 Romeo Charlie on his website to measure the characteristic impedance of a coaxial cable using nano VNA. For this, port 1 of the nano VNA is being used. 50 ohms dummy load and appropriate connectors and crocodile clips when needed are being used along with the Smith chart in nano VNA. This is a short patch cable, maybe around 30 centimeter, with SO239 connector at one end and the other end is PL259. I am trying to measure the characteristic impedance of this cable. This is a PL259 dummy load, 50 ohms dummy load, which I bought for calibration of the nano VNA some time back. This is the nano VNA. I have connected the jumper cable, SMA jumper cable, which is fitted with an adapter, SMA to SO239 adapter, so that it will fit into the PL259 here. The calibration here is from 1 megahertz to 11 megahertz. And when this is open circuit, you can, without a cable or anything connected there, you can see the SWR as 4.558. That's because there is no antenna connected, no dummy load connected. High SWR. Now the patch cable has been connected to the nano VNA. You can see that the SWR is still high because this is open circuit. There is no antenna connected, no dummy load connected. Now I have taken the Smith chart from the nano VNA menu. I have shown that in earlier videos. In case you want to see it again, I will show again. You will take the trace in the display. The trace 2 will correspond to the Smith chart. Now, what we are interested in the Smith chart is that the resistive component shown here, 50.69 ohms. 50.69 ohms is seen here. So we are supposed to check the resistive component when this marker is in the crossing line, that is in the center. So this is the resistive part. Now once you get this, what you have to do is multiply the impedance of this dummy load, that is 50 ohms, into this impedance, the resistive component noted on nano VNA, that is 50 into 50 will be 2500. And if you take the square root of that, you are going to get the characteristic impedance of this cable. But in this case there is a problem, because you get the answer as 50 ohms as the characteristic impedance of this cable. But as both are equal, we will doubt whether there is any error in the measurement. For that, we will have to check another cable with a different characteristic impedance. But as of now, what you have found is that from the calculation, when you multiply what is seen here, that is in the nano VNA 50 ohms approximately, and the known characteristic impedance, or rather resistive value of this is 50 ohms resistive component. This is also approximately 50 ohms resistive component. The reactive component is hardly anything, very little is the reactive component. So you will get 50 into 50, 2500 divided by, or rather square root of it will be again 50, the characteristic impedance of this cable. But I know that this is a 50 ohms cable which has been used as a patch cable for my radio for connecting the antenna. Now I have connected a much bigger cable. This is a 10 meter cable and dummy load has not been connected. and you can see that it's open circuit, and the SWR can be seen as quite high, as if the antenna is broken. You can see the SWR as 7.78. Unlike the other cable, this cable has a PL259 termination on both ends. One end has been connected, the other end cannot be connected to the dummy load because dummy load has PL259 termination. So I need a barrel connector. This is an SO239 to SO239 barrel connector which will connect between these two. It's an adapter. Now I have connected the barrel connector between these two so that the dummy load is now in connection with the 10-meter cable. Now you can see that the SWR has come to nearly 1.060. It is 1.060 at 5.1 megahertz. That will be there for other frequencies also, because you can see that the curve is flat. There is no difference with frequency across the 1 megahertz to 11 megahertz spectrum. SWR is 1. That's because this is just a resistive load here, dummy load. Dummy load will have a very good SWR, but it is not going to radiate your signal. Once again, as shown earlier, I have recalled the Smith chart. Here you can see that again the resistive component of the impedance in the Smith chart is exactly at the midline. Resistive component is 49.32. That is approximately 50. Suppose you multiply this with this 50 with the 50 of the dummy load, then naturally the square will be the value will be 2500, and square root will be again 50 ohms, meaning that the characteristic impedance of this cable is 50 ohms. So far we have tried only two 50 ohms cable, which we already know, but you are just counter checking. Suppose you have an old stock in which you do not know the characteristic impedance. This is a method of identifying the characteristic impedance. Next, I am trying to measure the impedance of this piece of cable, which is RG6, as you can see, and it's a very small piece. You can see again hardly 30 centimeter, but I have a problem. There are no connectors at either ends, so it will not be as simple as I did earlier, but I hope to use these different types of crocodile clips for connection. And I know that these long wires will induce some inductance, but I hope that as I am going to read only the resistive component in that nano VNA, that may not cause much of an error. Anyway, I am just trying it. I have just connected the dummy load to the cable. Central connector has been connected with crocodile clips with a short length of wire. The outer conductor or shield has been connected directly using another short crocodile clip. Now the connection is complete at both ends. Even though it's not a very perfect connection, it has been completed. And now we will see the measurements. You can see that the SWR is higher for this half-hazard connection. That is 1.7. Ideally, you would have expected 1:1 SWR, as it is a dummy load being connected. So this connection method is not very perfect. Still, I can show you the difference. You can see that the resistive component of the impedance is different. You can see it here. It is 89.52. We will take it as 90 itself for simplicity of calculation. If you multiply 90 with 50, that is the characteristic impedance, or rather resistive component of the dummy load, you will get 4500. And if you take the square root of 4500 as before, you will get approximately 67 as the impedance value. and that does match fairly well with the characteristic impedance of RG6 cable. RG6 cable is supposed to be 75 ohms, and you have to give a margin of error for me for using such haphazard connections, which are not the ideal way. I should have used much better soldering or something like that to connect this, and giving that margin of error, I think that should be a really acceptable situation. As an acknowledgement, I thank Sierra 21 Romeo Charlie for telling me this method on his website. I learned this method from the website of Sierra 21 Romeo Charlie.